Okay, well, hello everyone, and welcome to the IAMP One World seminar, which is a seminar series that's run by the International Association of Mathematical Physics. We're finally back for the year with a very exciting talk by Daniel Spiegel, who's going to be telling us about phases of matrix product states. Daniel, please take it away.
Thank you very much for the introduction. Thanks to the organizers for inviting me. It's an honor to speak in this seminar. Um, so this is the employment section of my CV. I'm currently at Harvard. This work was done while I was at UC Davis, and all of my collaborators you see here are at UC Boulder, or CU Boulder, which is where I did my PhD. Okay, so I was supported by the NSF while doing this. So this is going to be a talk about topological phases of quantum systems. And topological is going to be meant literally in a variety of different ways. So I'm first going to give some intuitive background about what I want you to be thinking of when I say topological phase. And then I'll try and define my terms as best as I can. And then I want to construct what I call a classifying space for phases of matrix product states. And I'll try and give you that construction as rigorously as I can and give you some analysis, some details of the analysis of its topology. Okay, so I want to think about quantum systems. And I want not just to think about one quantum system at a time, but I want to think about families of quantum systems. So I'm interested in families of ground states, psi x, that depend continuously on this parameter, little x, which lies in a topological space, big X. And typically there's going to be a gap in the Hamiltonian that's uniform in X. So I'm thinking of unique gapped ground states, depending on some parameter, little x. So this parameter space, capital X, typically will be some very nice, smooth, finite dimensional manifold. If you want, you could think about it as some external parameters that some experimenter is varying in their lab to change their system. Okay, so that's the sort of system that we're thinking about. And we want to talk about phases of parametrized families. So usually when we talk about phases of quantum systems, we say two quantum systems are in the same phase if one can be deformed into the other along a path where the gap in the Hamiltonian stays open along the path. Since here I have not just one quantum system, but a family, the notion of path needs to be replaced with homotopy. So I'll say two families are in the same phase if there exists a homotopy in some sense from psi 0 of x to psi 1 of x, and that there's a gap uniform in t and x. Okay, so that would be one way that they could be in the same phase. I want to enlarge that notion of phase. I want to also say that they're in the same phase if one can be obtained from the other by stacking with a trivial constant family. So I could say they're in the same phase if there exists a product state, omega, constant in x, or not depending on x, such that psi 0x tensor omega is psi 1x. Another way they could be in the same phase is if they're just presented differently. So maybe they're presented on isomorphic Hilbert spaces or something. So we'd say that they're in the same phase if there exists a constant isomorphism U, independent of x, that takes one family into the other. Okay, so these are a bunch of relations on families of quantum systems, and phase is the equivalence relation generated by all these relations. So I could do any combination of these, any finite sequence of these operations in any order. Okay, so this defines a notion of phase. And it's sort of a generalization of the usual notion of phase. The usual notion of phase is when the parameter space capital X is a point, then we only have one system. Or I could get SPT phases by introducing a symmetry. In SPT phases, symmetry-protected topological phases, the notion of phase, the classification of phases is enhanced by that presence of the symmetry. It protects some phases. And here, what's interesting about this parametrized phase is that the phase will be protected by the global topology of the space capital X. So we want to classify phases. This problem is interesting even without symmetry, so that's the only case that I'm going to deal with here. And the phase invariants are going to be topological invariants of this parameter space. Okay. So this was a little bit intuitive. In 0D, it's very easy to make this rigorous. So in 0D, usually I'm going to be, for most of this talk, I'm interested in many body systems, but the 0D, few body system is a useful analog. So in 0D, a parametrized system is just a continuous map from this parameter space into the projective Hilbert space of some finite dimensional Hilbert space. I'm going to be dealing with spin systems, so my Hilbert space is going to be finite dimensional. All right, so an example, textbook example, that hopefully everybody has seen at some point. We can take the parameter space to be the two-sphere, S2. We can consider a single qubit, so H will be C2. And we could look at the Hamiltonian H of R equal to R dot sigma, where this sigma is a vector of Pauli matrices. So this is a parametrized Hamiltonian. We could look at the ground states. The ground states cannot be written as a continuous map into the unit sphere of C2, but it can be written as a continuous map into the projectivization of C2. Okay. And then we want to ask, what's an invariant of that family? What's a phase invariant of that family? And one way to get a phase invariant is to look at the Berry curvature. It's given by this expression, where theta and phi are the polar and azimuthal coordinates. And to get an invariant, we could integrate the Berry curvature over the whole two-sphere. This is quantized, and this gives us a phase invariant. So it's invariant under all those operations. So another way to think about this, if you prefer, is that you could think about this ground state map as forming a line bundle over the base space X, the parameter space X. And this phase invariant is the first Chern class of that line bundle. Okay. So I'm going to be wanting to think about many body systems. And the question is there any sort of analog of this for many body systems? And there's a conjecture about this by Alexei Kitaev that he gave in a series of talks. Most recently, he gave talks about this conjecture just a couple months ago at Harvard. Those are online. You can look them up on YouTube. As are all these talks. You can all see them online. But the conjecture says that for each spatial dimension D, there is a space, a topological space, of gapped invertible spin systems, which I call QD. So this word invertible, it means that you can stack with another system so that it becomes a trivial system, but it's not going to be too important for this talk. So we're only going to be dealing with invertible systems here. Okay, so for each spatial dimension D, there is a space of gapped invertible spin systems called QD. These spaces should form a loop spectrum. So the space QD should be weak homotopy equivalent to the loop space of QD plus 1. Okay, again, I want to make this talk friendly even if you're not an algebraic topologist. So we're not going to be dealing with loop spectra here, or any sort of fancy algebraic topology, the part of the conjecture that I want to focus on is that Kitaev gave predictions for what these QD spaces should be. So for 0D systems, it's well understood that this Q0 space should be an Eilenberg-MacLane space of type KZ2. So what that means is that the nth homotopy group of Q0 is Z if n is 2, and it's 0 for all other n. And this is well understood, and I'll explain it in the next slide. But he also conjectured that Q1 should be a KZ3. And that's going to be where I really want to give my main results about. So I'm going to try and construct a space that deserves to be called Q1. This is the space of one-dimensional gap spin systems. And then we're going to try and analyze its homotopy types. So KZ3 means, again, in degree 3, its homotopy should be Z, in all other degrees 0. Okay, so the upshot of this is that these homotopy types give us a classification of parametrized phases. So phases of d-dimensional systems parametrized by a space X are classified by homotopy classes of maps into this classifying space QD. So this square brackets means homotopy classes of maps from X to QD. So in particular, 0D phases are classified by H2 of X, and 1D phases should be classified by H3 of X, the third degree cohomology. Okay. So how does this Q0 space come about? So how would we construct it? So up to isomorphism, any 0D system looks like a map into PCM. So any finite dimensional Hilbert space, I can write it as CM up to isomorphism. And then when we do this operation of stacking, we, up to isomorphism again, are just increasing the dimension of that Hilbert space. So there's a natural inclusion of PCM into PCN where I just add zeros to a vector, and that's what stacking is up to isomorphism. Now we want to allow for an arbitrary amount of stacking, so we would take this n to infinity. And that's how we get this classifying space. So Q0 is going to be PC infinity, a co-limit of these PCNs. And I can understand this relation of phase with this following little proposition. So if X is a compact parameter space, then two systems are in the same phase if there exists a unitary, or if there exist two unitaries from their Hilbert spaces to CNI, such that when I look at these maps, I look at my system, I compose with this unitary, and then I include into PC infinity, those two maps are homotopic. So the point is, I can think of any parametrized system as a map into PC infinity. And once I think about it that way, stacking and isomorphism are already taken care of, and the only thing left to take care of about the phase is homotopy. Okay. So we've concluded that this Q0 space should be PC infinity. And how do we understand its homotopy type? So we can, so PC infinity is this colimit of PCNs. These PCNs are state spaces. But when we actually describe a quantum state, we usually write it as a normalized vector in a Hilbert space. So we usually write it as an element of the unit sphere of a Hilbert space, which I denote by S for sphere of the Hilbert space C2. So there's also a colimit of these unit spheres. And the unit sphere here, the colimit I denote by SC infinity. So this top row is some space of gauge data. There's this unphysical U1 phase, the bottom row is the space of actual states. And all of these vertical arrows are U1 fiber bundles. And that fiber bundle gives me a way to analyze the homotopy type of the colimit, the classifying space, PC infinity. And the way I do that is I first note that the colimit of the gauge data, SC infinity, is actually a contractible space. And then I use the fact that this is a U1 fiber bundle to get a long exact sequence that looks like this on the homotopy groups. So here we've got the total space, which is the sphere, the base space, which is C infinity. Then we go down a degree in homotopy and we get the fiber, U1, and then we go to the total space again. But SC infinity is contractible, so these homotopy groups are 0. And I get that the homotopy groups of the classifying space PC infinity are just one shifted from the homotopy groups of the unit circle U1. And U1 is a KZ1, so PC infinity is a KZ2. Okay. I want to know if this story generalizes, or I want to show you that this story does generalize for many body systems. Before I do that, let me mention some literature about these many body parametrized phase invariants. There's a lot, and I haven't listed everything here, but let me just remark about some highlights. This H3XZ invariant, which is the phase invariant that classifies 1D spin systems. This was introduced or first analyzed by Kapustin and Spodenko as a higher form Berry curvature. And later work was done on this by Kapustin and Sopenko and Artemovich, I think is the correct pronunciation. More work was done on analyzing that Berry curvature, higher Berry curvature, showing how to get it from ground states, showing it was quantized. Our group at University of Colorado Boulder also did work on this phase invariant. So we showed a bulk boundary correspondence, interpreted this higher Berry curvature as a flow of lower dimensional Berry curvature, gave examples, which I'll give later in the talk. My PhD thesis has a C-star algebraic derivation of this H3XZ invariant in a similar style as Ogata has derived SPT invariants. And then later work analyzed specifically this matrix product state setting, which I'll be talking about, and constructed this H3XZ invariant in various ways. But this paper that I'm talking about today gives the first concrete construction of a classifying space, this Q1 space, specifically for MPS. So shortly after our work came out, Kubota also gave a more abstract construction of Kitaev spectrum. So it'll be very interesting to compare our methods in the future. But for this talk, I just want to focus on giving a concrete construction of this classifying space for 1D spin systems. Okay, so my setting is going to be infinite spin chains. When we're talking about phases, it's often nice to work in the thermodynamic limit. So that's what I'm going to do. I'm going to talk about translation invariant systems, translation invariant infinite spin systems. So formally or rigorously, how do we define such a system? So for each point in the lattice, I'm going to assign the finite dimensional Hilbert space Cn, describing a spin at that point. And since I want to consider translation invariant systems, I assign the same Hilbert space at all points. Then rather than taking some infinite tensor product of Hilbert spaces, I'm going to focus on the observable algebra. So I do this in the C-star algebraic framework, if you're familiar with that. If not, I'll try to explain. So for each finite subset of the lattice, we can take a finite tensor product of these matrix algebras that describe the observables on site V. And I can embed all of these finite dimensional algebras in some big infinite tensor product of observable algebras. So I call this the local algebra. The local algebra with on-site dimension n is the span of tensors, which are infinite tensors, but their identity after finitely many points, finitely many sites. So this is the local algebra. It's a normed star algebra, and I can complete it to get what's called the quasi-local algebra. So this is now a nice C-star algebra that describes the, well, quasi-local, almost local observables of my spin chain. Okay, but I want to talk about states. I want to talk about matrix product states. So what is a state in this framework? There is no Hilbert space to talk about yet. Rather, we think of states in terms of their expectation values on observables. So a state on this infinite spin chain is a linear functional from the quasi-local algebra to the complex numbers that satisfies a positivity condition. So omega of C star C is greater than or equal to 0 for all C and N, AN. And it satisfies a normalization condition. So omega of the identity should be 1. And I'm going to be talking about pure states because unique ground states of gapped Hamiltonians are pure. So a pure state, a state is pure if it cannot be written as a non-trivial convex combination of other states. So if I write omega as a convex combination, it must necessarily be trivial. So this t is either 0 or 1, or if this t was in the inside of the unit interval, then all the states omega 1 and omega 2 would have to be equal to omega. Okay. And for notation, I will denote the pure state space of AN as Pn. All right. So this pure state space is quite large, and I want to restrict myself to a specific subspace of matrix product states. So a matrix product state is described in terms of a tensor, which for me is just a collection of complex numbers, which I denote by ki alpha beta. It has 3 indices. This top index is called the physical index. It ranges from 1 to the dimension of the on-site Hilbert space, n. And these bond indices range from 1 to some internal dimension chi, which I will be calling the essential rank. We'll have a different dimension later that we'll call the bond dimension. So this chi is going to be the essential rank. And I'm going to consider tensors with 2 other special properties that just make this analysis quite nice. We can consider states without these properties, but with them the analysis is much simpler. So a tensor is called right normalized if the sum from I equals 1 to n of these ki star matrices is the chi by chi identity matrix. So here I'm dropping the bond indices, so I'm thinking of ki as a chi by chi matrix. And I say the tensor is injective if the span of all the ki matrices is all chi by chi matrices. Okay. So this is a tensor, it defines a state. And if you're familiar with matrix product states on finite lattices, you might be familiar with an expression of this form, where I1 indexes the standard basis on site 1. So the coefficients are a trace over a product of these matrices. That's why it's called a matrix product state. But on an infinite lattice, we can also define a state. I have to tell you how it acts on observables of arbitrary size. And so the way it does that, I've given you this expression here. It's a bit long, but you can show that this defines a positive linear functional. this T matrix here is the only thing I haven't defined. This T matrix is the unique positive definite matrix such that the sum from I equals 1 to n of ki star t ki is equal to t, and the trace of t is 1. So given an injective right normalized tensor k, that such a T matrix exists and is unique is a theorem, or follows from a theorem of Evensen-Hogg-Krohn, and states, these matrix product states in the thermodynamic limit were first considered by Franz Nachtergaele and Werner in '92. Okay. So these tensors are like the top row of that 0D ladder diagram. They're sort of how I describe the state, like a unit vector in a Hilbert space. It's sort of like gauge data. There's a little bit of redundancy in that description. What I'm really interested in writing a classifying space for is the states themselves. And so we can ask how much redundancy is there in this description of states in terms of tensors. And this is answered by, again, a theorem of Franz Nachtergaele and Werner on the infinite lattice, or if you want to think about finite lattices, there's an adaptation to by Perez Garcia, Frustrata, Wolf, and Sirac. But this is called the fundamental theorem of injective MPS. And it tells us how much freedom there is in this description of states via tensors. So it says, let K and L be two injective right normalized matrix product state tensors of physical dimension n. They both have the same physical dimension, and bond dimensions chi K and chi L. Then they define the same state if and only if they actually have the same bond dimension, or essential rank, excuse me. And there exists a phase, lambda in U1, and a unitary U in U chi, such that each Li matrix is of the form Li equal to lambda U Ki Ui star. Okay. So one thing that's interesting about this is that this bond dimension, or clearly I'm getting mixed up saying bond dimension and essential rank, but I'll try and say essential rank chi. This is a property of the state. All right. So again, these tensors are our gauge data. The state is what we're really interested in. And this fundamental theorem tells us what our gauge freedom is. All right. So I'm going to try and construct a classifying space for these MPS states. But first, let me try and give an example. So this example was given in works by this Boulder group. It has 2 qubits per site, so the on-site dimension is 4, and the parameter space is the 3-sphere. So this little dotted red line here is one site. It's got 2 qubits, so there's an A and a B sublattice, and this colored ball is the 3-sphere. And we'll write elements of the 3-sphere as a vector W, which has 3 components, and the 4th component W4. So the Hamiltonian is a sum of 3 terms. This first term is the 0D example we had on the second slide, with an alternating sign on the magnetic field alternating between the A and the B sublattice. So the direction of that magnetic field depends only on the first 3 components of this vector in S3. Then we've got a term that couples qubits on the north hemisphere and a term that couples qubits on the south hemisphere. And the way they're coupled alternates. So in the northern hemisphere, we couple intersite. We couple B on site n plus 1 to A on site n plus, we couple B on site n to A on site n plus 1. And in the southern hemisphere, we couple intrasite. So we couple A and B on the same site. And this interaction, this north interaction gets turned off as we go to the southern hemisphere, and the southern interaction gets turned off as we go to the northern hemisphere. So this is a very simple example if you consider it point by point. It's just decoupled into dimers. But as a family, it's non-trivial. It's in a non-trivial phase. And we can show that. Well, we did show that in these papers, and I'm going to give another argument as well. But what's interesting about this example is that the bond dimension changes. So this is a ground states, unique ground states of a uniformly gapped Hamiltonian. The bond dimension, however, changes discontinuously as I turn on the coupling between sites. So when there's no coupling between sites, the bond or the essential rank is chi equals 1. And when there is coupling between sites, the essential rank is chi equals 2. So I need to construct my classifying space in a way that allows me to change bond dimension.
So Daniel, what is GN, GS? Are they arbitrary?
GN,
Except for the
they're arbitrary continuous functions that should be
zero.
Not zero. They need to turn on at some point, but they're yes, they can be arbitrary continuous functions. Or if you prefer to have an explicit example, that was given in our papers up here. But I think in my thesis I analyzed it for arbitrary continuous G.
Thanks.
Okay. So let's construct this classifying space. And we're going to start with the tensors, and then we're going to mod out by the gauge freedom. So it's like we're starting by constructing SC infinity if we were doing the 0D case. So I start with the tensors. I'm going to start by taking the bond dimension and the physical dimension to infinity, because I want to allow for arbitrary stacking. So I should take the on-site dimension to infinity. And I also have this new dimension, the internal bond dimension, to consider. So I should take that to infinity as well to capture all possible matrix product states. So I could consider tensors that look like, I put this injective tensor in the corner, I add zeros everywhere, and I consider an infinite list where eventually this list is 0. But that's not going to work for me because it won't allow me to change bond dimension. The bond dimension here is the bond dimension, if I consider tensors like this, is a continuous function. And so it will just disconnect my space into different pieces for the bond dimension. I won't be able to jump between bond dimensions. So I have to do something. I have to modify these tensors or consider more general forms that allow me to change the bond dimension, like we had in the example. So I consider tensors instead of this form. So U, K, M, 0, 0, U star. And the state defined by K is still recoverable from such a tensor. But this is a general enough form to at least capture the example I showed on the previous slide. In a neighborhood of any point of S3, there is a continuous representation in terms of tensors like this. That's not true if I had just considered tensors of this more primitive form. Okay, so I'm going to consider tensors that look like this. Eventually, these Ki and Mi matrices are 0 after finitely many, they only have finitely many non-zero entries. And this U here is an infinite unitary matrix. So eventually it looks like 1's on the diagonal and 0's everywhere else, but maybe it has some non-trivial piece in the upper left corner. So everything here should be considered as an infinite matrix with finitely many non-zero entries. Okay. So the classifying space for the tensors, or the space of all tensors, I again construct as a colimit of sort of finite dimensional subspaces. So for a finite n and a finite d, I define the space of tensors E and D to be the set of all tensors of the form shown on the previous slide that are 0 in entries where I is greater than n or alpha is or beta is greater than d. So this E and D is just a subspace of a finite dimensional vector space. So it has a natural topology on it. And all these E and D spaces include into a colimit. And I give this E the colimit topology. So I topologize it with the finest topology such that all the inclusion maps from E and D into E are continuous. All right, so I want to define a space of states. So I should quotient by gauge transformations. And here a gauge transformation means, well, guided by this fundamental theorem of MPS, I know I should be able to conjugate by unitaries and change an overall phase. And there's also this M matrix that does not affect the state. So I should be able to change that too. So a gauge transformation for us takes a tensor that looks like this and changes everything, the overall phase, the unitary, this M matrix, it changes it to an N, but it keeps this injective right normalized MPS K the same. So this defines an equivalence relation on each E and D, and it defines an equivalence relation on E. And to get the space of states, I just mod by that equivalence relation. So B and D is the quotient of E and D by this equivalence relation. I give it the quotient topology. And the colimit B, well, I can think of it as a quotient of E by this equivalence relation, or I can think of it as a colimit of B and Ds. And the quotient topology coincides with the colimit topology. So there's a natural topology to give on this space B. So this is my classifying space. So we're going to identify B as this desired classifying space Q1. All right, so what I've done here is I've constructed this diagram analogous to the 0D case, where we have spaces of tensors, that's like our gauge data, spaces of states, and it forms this ladder diagram. And just to be sure that this B deserves to be called a space of states, I just want to summarize what we've done in this proposition. So this map that takes a tensor and sends it to a pure state of the quasi-local algebra, it takes this tensor and it maps it to omega k. That is a well-defined map, even though k is buried in this tensor. I can still recover the state omega k. This is well-defined, and it factors through an injective map from B and D to the pure state space of the quasi-local algebra. So when I did this mod by gauge equivalence, I did capture all the gauge equivalents, so this map became injective. So really this B and D can be thought of as a space of pure states. Okay. There's an interesting aside to be made here. So this proposition, we have a diagram, a triangle diagram that looks like this. I map tensors to the corresponding state, and it factors through this B and D space. Pn already has a topology on it, or it has a number of sensible topologies, but one of them is the weak star topology. So Pn is a subset of the dual space of the quasi-local algebra, and you can consider the weak star topology on it. These maps are continuous into Pn with the weak star topology. But it was a little surprising to us that this map from B and D to Pn is actually not a topological embedding. So the topology on the space of states, of matrix product states, is strictly finer than the weak star topology. And there's a counterexample or a reason to, a way to see that. We have a path of states given below in terms of their tensors. This is a a weak star continuous path in P4, but it's not continuous in the topology of B42. So on-site dimension 4, bond dimension 2. And the way that you can see that this is not continuous at s equals 0, well, for all s not equal to 0, this is a well-defined injective right normalized tensor. But at s equals 0, it's no longer of the allowed form for our tensors in E. So for all s not equal to 0, this is a tensor in E42. At s equals 0, it's not a tensor in E42 because we have a 1 here and a 1 here. And the proper way to represent this as a tensor in E42 is with a 0 in the bottom right corner, not a 1. So there's sort of a discontinuous jump in this representation. Let's see. Okay, so let me try and say it correctly. So every state along this path can be represented in E and D, but the representation is discontinuous in E and D at s equals 0. And it's discontinuous in B and D as well. You can look at the sum of the absolute value of the traces. This is a continuous map on B42, and it has a discontinuity at s equals 0. Okay. So let me move on and talk about our main results. We constructed this classifying space. We want to analyze its homotopy type. And Kitaev conjectured that it should be a KZ3. For us, it's actually not a KZ3 because we considered sort of a restricted class of states. We considered only translation invariant states. But here are our results. There's a direct analog of the story for 0D for 1D. So first of all, this colimit of gauge data is contractible, just like SC infinity was contractible. Then we can analyze the fiber. For 0D systems, the fiber is U1. All these are U1 fiber bundles. For these 1D matrix product states, the fiber changes over points of different essential rank. So if omega is a state of MPS represented by an injective MPS tensor with bond dimension chi, or essential rank chi, then the fiber is homotopy equivalent to U1 times the projectivization of the Stiefel manifold of chi frames in C infinity. So that's this V chi C infinity. Orthonormal chi frames in C infinity. And this is a KZ1 times KZ2. So in the 0D case, we then were able to analyze the homotopy groups of B by a long exact sequence because we had a fiber bundle. We no longer have a fiber bundle in the 1D case because the fibers are not homeomorphic over different points of the base space. But it turns out that this projection is something called a quasifibration. And a quasifibration also has a long exact sequence. So we can similarly analyze the homotopy groups of B, and we find that it has the weak homotopy type KZ2 times KZ3. So we do get this KZ3 piece that Kitaev conjectured. We also have a KZ2 piece that's sort of left over from the 0D story and coming from this U1. It's sort of a 0D phase invariant that carried over to these translation invariant states. Okay, so I would like to give some details of how we proved all these theorems. There's like 4 theorems in one here. So there's the contractibility of E, there's the analysis of the fiber, they're showing that this map is a quasifibration, and then there's the analysis of the homotopy type of the base space. I will go through two of these things. I want to show you why is the fiber U1 times PV chi C infinity, and I want to discuss why P is a quasifibration. The contractibility of the space E is sort of similar in spirit to the contractibility of SC infinity. So for a lot of these contractibility proofs, what you do is you sort of homotopy things so that you shift things down and you free up some space. Like in SC infinity, you have infinitely many components, so you shift your vector down in components, and now you've freed up a component at the very beginning and you sort of contract into that free component. The proof that E is contractible is sort of similar in spirit. It's more complicated since we're dealing with a more complicated type of space, but I think I will skip it for time. So let's talk about the analysis of the fiber first. Okay. So let's look at the fiber over a point omega in curly B with essential rank chi. It can be represented by a tensor which has a very simple form, k is 0, 0, 0. So the m here is 0, and the unitary that gets conjugated, or the conjugating unitary is the identity. You can always represent a tensor like that. Now the fiber over this point is the set of all tensors that look like lambda u k, any m, and then u star. So this is all the tensors that map to omega. And you see that we have a surjection. So we have a surjection from u1 times u infinity times m infinity by chi matrices, and there's infinitely many of them. So that's this m. So this is the lambda, this is the u, this is the m. So there's a map from triples of lambda, u, and m to this fiber, and it's a surjection. But there's some redundancy in that description. So it's not an injection. So two triples that are related in the following way will map to the same point. So if I multiply u on the right with some infinite unitary, which looks like a scalar multiple of the identity in the top left corner, followed by an arbitrary infinite unitary. And I also multiply m on the left by that scalar phase and v star. Remember, m is the infinity by chi matrix, so I can multiply it by an element of u infinity. So if I act in that way on this triple, I will map to the same state. Or sorry, I will map to the same tensor. I will map to the same element of the fiber. So this is an action of u1 times u infinity. It's acting on the right of this u infinity component, and it's acting on the left of this m component. And when I quotient by that action, I get this balanced product. And now I have a bijection onto the fiber. So this is a description of the fiber. The fiber is homeomorphic to u1 times u infinity times m infinity by chi to the infinity mod this balanced product, or mod this group action. Okay, and to be perfectly honest and technical, I should say that we actually showed that the fiber is homeomorphic to a colimit of these spaces, where you first replace all the infinities by finite numbers and then you take a colimit. But the idea is the same. Okay, so then I can represent points in this fiber as triples, lambda, and then an equivalence class of pairs u and m. Okay. So this fiber doesn't look anything like what I promised yet. I promised you PV chi C infinity. Fortunately, this M piece here is contractible. So up to homotopy, I can kill it. So the fiber retracts onto this M equals 0 subspace just by scaling the M matrix to 0. That's a well-defined deformation retract. And then all I'm left with is U with an action of U1 times U infinity, which I've displayed here. This V matrix is acting on the chi+1 to infinity columns of U. And when the orbit of this action forgets about those columns. It only remembers the first chi columns of this U matrix up to the phase mu. So that's where the Stiefel manifold comes from. It's the first chi columns of U. So rigorously what we showed is that the map from the fiber to U1 times PV chi C infinity that takes this triple lambda UM and maps it to lambda and then this chi tuple of columns. This is a homotopy equivalence. And so now we know that this fiber is homotopy equivalent to U1 times PV chi C infinity. We know that PV chi C infinity is a KZ2 because I can construct another fiber bundle with V chi C infinity as the total space, the fiber being U1, and V chi C infinity is contractible. So by a long exact sequence, I get that PV chi C infinity is a KZ2. Okay, so that's the fiber. Now the real hard part is showing that this is a quasifibration. And what is a quasifibration? This was introduced by Dold and Tom in '58. And you can also read about it in Hatcher's algebraic topology textbook. But a quasifibration is sort of a generalization of a fibration or a fiber bundle. So a continuous map is a quasifibration if for all points of the base space and any point in the fiber of that base point, the induced map on homotopy, which I call P star, is an isomorphism or a bijection for all n greater than or equal to 0. So this group in the domain is a relative homotopy group. And if you don't know what that is, that's okay. The point is, with a quasifibration, or the definition of a quasifibration is designed to be exactly what we need to get a long exact sequence. So if P is a quasifibration, then I get a long exact sequence, where F is the fiber, E is the total space, B is the base space, and it goes down into, I think I did this wrong. So this should be n plus 1. And this should be an n. Okay, little typo. All right, how do I show something as a quasifibration? I certainly do not check directly from the definition. Dold and Tom also give us a better way to show something is a quasifibration. So there are essentially 3 ways, and I'm going to use all 3 put together. So a map is a quasifibration if any of the following hold. I can write the base space as a colimit of a sequence of subspaces, and P is a quasifibration restricted to any of those subspaces. That's way number 1. Way number 2 is that I write B as a union of 2 open sets, and P is a quasifibration over each of those open sets. And way number 3, which is the most complicated, is that there exists a subspace, B prime, of the base space B, such that this space E prime, which is the preimage of B prime, okay, P is a quasifibration from E prime to B prime, and there exist deformation retracts, H, capital H and little h, from E onto E prime and from B onto B prime, such that these deformation retracts are compatible with the projection. They commute with the projection. And such that at the end of the deformation retract, at time t equals 1, this capital H is a weak homotopy equivalence on fibers. All right. So how do we apply this to our spaces of MPS tensors and MPS states? Should just say MPS. The S in MPS stands for state, so I shouldn't say MPS states. Okay. So we use way number 1 first. We write B as an increasing sequence of subspaces. This time, not filtering by N and D, but rather by chi, the dimension of the K matrix. So we write B as an increasing union of a sequence of subspaces where B, E less than or equal to chi and B less than or equal to chi are the set of those tensors or states with essential rank less than or equal to chi. So now the goal is to show that each of these vertical maps is a quasifibration, and I do that inductively. So assuming I can show that one vertical arrow is a quasifibration, I show that the next arrow is a quasifibration. And to show that, I use method number 2 from the slide before. I write B less than or equal to chi as a union of 2 open subspaces. So the first subspace is just the set of states that are with essential rank equal to chi. That's an open subset of B less than or equal to chi. And the projection map, when I have fixed essential rank, is the serifibration, actually. In this case of a fixed essential rank, it was first studied by these authors. And so we sort of adapted their results to our bigger tensors, our infinite dimensional tensors. All right, so then all we need is an open set. We need our second open set. This would B equal to chi was our first open set. We need another one, and we need to cover B less than or equal to chi. So what we do is we find a saturated neighborhood, O less than or equal to chi, of E less than chi, strictly less than chi. And we show that this O less than or equal to chi retracts onto E less than chi in a gauge invariant way, so that the retraction up top in the space of tensors will descend to a retraction in the space of states. All right. So I realize I only have 2 minutes. I'll just very quickly say what this space with this O less than or equal to chi neighborhood is, and what the retraction is. Both are defined in terms of this matrix L of A. L of A is a function of the tensor. It's not a continuous function, but it's a positive matrix with rank chi. If A has essential rank chi, then this L of A matrix has rank chi. And so my neighborhood is going to be the set of those tensors with bond dimension less than chi, and also those tensors with bond dimension equal to chi that have a small eigenvalue. So they have at least 2 distinct eigenvalues, 2 distinct non-zero eigenvalues. One of them I'm thinking of being small, because if I leave E less than chi to go into E equal to chi, I'm basically sprouting a small eigenvalue of this L of A matrix. So this is a neighborhood of E less than or equal to, a neighborhood of E less than chi. And I'm out of time, so I'll be very quick. The idea of the retraction is to just take that small eigenvalue and push it back down to 0. So when I do that, I reduce the essential rank from chi down to something smaller, strictly less than chi. Here's the formula, but I'm out of time, so I won't explain it. Okay, let me just jump to our conclusions. we have this, we constructed this classifying space for injective matrix product states. The analysis was very nice because we restricted to a very special class of states, these translation invariant injective MPS. We were able to show that the classifying space is a KZ3 times KZ2. So not quite what Kitaev conjectured, but that's because we restrict to a very special class of states. And there's many directions that we can go from here. So can we construct a classifying space for more general states? Can we construct classifying spaces with symmetry? Can we do it for higher dimensional systems? And how do these fit into a loop spectrum, which is what Kitaev conjectured? Okay, I'll stop there. Thank you very much for your time.
Well, thank you very much, Daniel, for this lovely talk. We have time for some questions. If you have questions, feel free to unmute yourself and ask, or you can write them in the chat, or you can use the raise hand feature if you prefer.
Well, Daniel, very, very, very nice talk. I've been exposed to this work many times, and I think it's really a wonderful piece of work. And this talk really laid it out very nicely. Well, you have your conclusions here, and the one thing was I'm curious about most directly is at this moment, what can we say about the higher dimensional systems, say two-dimensional systems, for example? Can you summarize what's known?
I can summarize what's conjectured. So what's conjectured is that this Q2 space is supposed to be Z times KZ4. So this KZ4 piece comes from sort of suspending the KZ3 piece of the 1D systems. So I think we understand how to construct, say, a system over S4 that has non-trivial H4XZ invariant. And I will, so Oyama and Ryu actually have a paper on constructing H4XZ invariants for 2D PEPs. This Z part is more mysterious. This Z part is supposed to correspond to stacking with Kitaev's E8 phase, which I don't think there exists a lattice model for. But I do think that Nikita Sopenko has a recent paper, or has done work on how might you construct a phase invariant for that, for a system that's in that phase, even though we don't have a lattice model for that phase. So this is related to chiral central charge. I think that's the best summary I can give for your question.
Okay, there is some work left to do, it seems.
Clearly, yes.
So,
Are there any further questions?
yeah, can
Yes.
I ask a not very sophisticated question? So going back to the original motivation, the motivation was to classify these parametrized phases, right?
Yes.
So the simplest example I can think of is to choose X not as a point, but X as S1, for example. And then this is sort of problem like Thouless pumping in condensed matter, right? So what does your general theory say for the classification in this case? You can take this kind of commutator-like thing with your thing. And
so for spin systems,
yes.
the only invariants are in H2XZ and H3XZ. So if you take X to be S1, you will get no non-trivial invariants. However, you could do this with symmetry. If you introduce a symmetry, then you will get non-trivial invariants. And this was done specifically for S1, systems over S1 with symmetry. This was done by Bachmann, Frost, Japanese, I think. I don't know how to say the name, but and maybe one other author that I'm forgetting. So this is a sort of a Dallas pump. You can also do sort of a pump. You can also take x to be S2 times S1. That has non-trivial degree 3 cohomology. So you can have a pump of this 0D example.
Oh, yes. Oh, how do you pump 0D?
This
Okay,
was done
that's funny, but okay.
This was done in the paper by Shweta Wen et al. From 2021. It's called like flow of Higher-Berry curvature. It's done in there.
Thank you. Yes.
Welcome.
Very nice. We have time for another question if there's one. If not, then let's thank Daniel again for this lovely talk.